Bismillahirrahmanirrahim. In the last class, we have told that we'll discuss about the Z transform to this session. Okay, I'll just march two consecutive lectures. One is Z transform, one is the basic filter design. So the few parts actually been taken from the undergraduate level as well as some part from the higher level as well. So I assume that you have a good idea, or at least the fundamental ideas on the Z transform, and you know the purpose of the Z transform. However, I just represent few things here before starting, and I would like to request you to review the Z transform, what you have learned from your bachelor background as well. Quickly, I just make the review of the Z transform today, and then of course about the filter design. How do we start our filter design with the help of the Z transform with respect to that? As you can know that in case of discrete domain, we are doing the Z transform, and in case of continuous time domain, we are doing the Laplace transform. So I believe that you have a very clear idea on the Laplace transform. This is very important for the signal processing. Mostly, if we just talk about the equation from the equation perspective, in case of Fourier transform, when we are doing the Fourier transform, this should be known as the continuous time Fourier transform. In that case, we are using e to the power minus j omega and e to the power minus j omega t. Just to target the particular frequency, we want to know about the frequency component in the signal. However, in case of a Laplace transform, we are using e to the power minus s, where s is equals to sigma plus j omega. So omega should be written as the capital one. So e to the power minus st. So if we put substitute the value of s, we can find e to the power minus sigma t minus j omega t. So this is the Laplace transform. In case of continuous time Fourier transform, this is our value. We want to find the similarity with this with our unknown function xt. In case of Laplace transform, this is our checking function or the similarity function. We want to check this function with our xt. And hopefully you already know that what is the essence of e to the power minus sigma t. This actually gives us the phenomena of a sinusoidal signal. Let's say this is of course a sinusoidal signal. This is e to the power, so we can divide in two parts. So if I write e to the power minus sigma t into e to the power minus j omega t. So that means this part actually representing the oscillation. Let me talk about this, the oscillation, if depending on the value. So conventionally, this one, that means e to the power minus j omega t, for a particular value, this is a pure sinusoidal wave, whether this is a real part or imaginary part. Let's think about any part of that. So it will be a pure sinusoidal whenever the magnitude is 1. So I'm talking about e to the power minus j omega t. From there, you can took cos omega t minus j sine omega t. So if I just take sine part here, so this is a pure sinusoidal sine signal. where the magnitude is 1. Here the magnitude is 1. Now, if you multiply it with another value, so e to the power minus sigma t multiplied with sine omega t. So what does it mean? Here we have a multiplying factor. Depending on the value of alpha, the sigma, it might have 3 conditions. One is there is no deviation from the starting point, so it is known as the critically stable signal. Or it might happen that it will have higher value first and then it actually decreases with the time. So this is known as, definitely this is known as stable signal. So depending on the value of sigma. So the first one, this one, in this case, the sigma, definitely this is equals to 0. So there is no deviation. So when we have the deviation, that means it has the sigma value is a positive one, is more than 0. Sigma is more than 0. Actually, whenever we have the negative one, so it gives a deterioration from the starting value to the end. Or on the other hand, it might happen that it might give higher value than the previous. So this is, of course, an unstable situation of the sigma. So in this case, in the third case, the sigma is less than 0. Whenever this is a less than 0, negative, and negative makes positive. That's why this is an unstable situation. So there are three situations. In case of Fourier transform, we can only justify what is the frequency. That means we only target this value. We don't take care about the stability. So in case of in a Laplace transform, as you know that in the Laplace transform, so if the pole locations are in the negative plane, that means the alpha value. So let's say this is the alpha value. What is the value? Let's say this is minus 0.5. In that case, we have e to the power minus sigma t. This belongs to e to the power minus 0.5, so 5t. So you are getting some sort of sense by which you understand what is the how the signal is related to your stability. That means if your xt, now I am talking about xt, if the xt looks like a decaying function in a RLC circuit, let's say you have RLC circuit, what is the output of that? If the output looks like this, then of course this is a stable signal. Okay, so I have faced some internet issues, so maybe we can start again. Can you hear me? Are you there?
Yes, sir.
Okay, fine. So what we are discussing that in case of Laplace transform, we are targeting one extra term, that is the stability of the signal, whether the signal is stable or critically stable or unstable. So we are talking about the xt. If it is like this, so there are three sort of situation might happen. So it might happen that we have the signal and getting large, so this is unstable, or this is a critically stable. So in the three cases, we know that in the Laplace domain, what is the frequency? First of all, what is the frequency? That frequency actually been represented by this one. In case of Fourier transform, we have the frequency there. For this one, I should choose the capital one, capital omega, just to make that, because we are talking about the continuous one. So this omega scale, so let's say we are talking about this one. What is the frequency? Let's say we are getting the frequency somewhere else. If I put this is the 0, so we are getting some value here. So now this value actually been represented somewhere else here. So by putting a dot, so this one, this black one, this can be represented like here. Let's say the frequency of this one is also the same. Let's say this is the frequency omega 1, this is omega 1, and this is omega 1. So this is omega 1. But then now the problem is in the continuous time Fourier transform, we can't differentiate between these three from the stability point of view, and that's why it really matches. We are introducing extra term minus sigma t, where for the sigma value, we are getting, let's say for this one, we are getting this point over there with the same frequency, The frequency is this, but what is the value of alpha? This is the value of sigma. The sigma value is this one, and you are getting the pole location over there. And for this is unstable situation. So let's say we are getting that pole over there, and this is the value of sigma. So let me write it here, sigma 1, this is sigma 2. So this is sigma 1, and this is sigma 2. And for the third one, sigma 3, in that case, the value of sigma is 0, definitely. So we are getting the pole over this, because the sigma value, this is sigma 3, is there. So in a very precise format, what we have learned here, in case of Laplace transform, we jump from the Fourier transform to the Laplace transform just to represent the signal from the stability point of view. Similarly, whenever we are jumping from the discrete time Fourier transform to the Z transform, that is the main purpose is to show the stability of the system. So from the equation point of view, we are in the discrete time Fourier transform. We need a summation, definitely summation xn e to the power minus j relative frequency omega n, and that is the value. So of course the value alpha, n is from minus infinity to plus infinity. And in case of Z transform, we are doing the same thing. We are taking our unknown signal xn, and now we are multiplying a factor with r to the power minus n and e to the power minus j omega n. Again, n is equals to from minus infinity to plus infinity to capture the whole sequence. It can be also precisely, we can write it here, n is equals to minus infinity to plus infinity xn, and we can took the value r e to the power j omega, j omega whole to the power minus n. And this is known as the value of Z. So we can write in a precise format, n equals to from minus infinity plus infinity xn and z to the power minus n. Okay, as you can find here, we are introducing an extra value or constant, not actually a constant, it's related to the n value, which is also an exponential function. It can have, if you have if you can choose the value of R, by choosing the value of R, you can make three situations. One is critically stable, so there is no change, for which case, in that case, the value of R is equals to 1. So if you choose R is equals to 1, so it is exactly like the discrete time Fourier transform. If you choose the value of R higher or lower, depending on that, you can make this total scenario stable. Not exactly that one, even this scenario. This will be stable. That means if your signal xn, that is from n is equals to from minus infinity to plus infinity, this term is unstable, in that case, you can't do the Fourier transform, because the Fourier transform, to do the Fourier transform, the signal should be summable. So if the signal is not summable or square summable, in that case, you can't do the Fourier transform. We have talked about this. However, you can introduce this r to the power minus n. You can choose this value of r in such a way so that the system can be stable. And that actually represent the ROC of the Z-plane representation. So let's say for any arbitrary input xn, if for r is equals to 2 and more than 2, so from 2 to infinity, that is the range of r for which the xn, that means the signal, is stable, or you can say the system is stable, then how we can represent that thing? Let me draw a circle here where this value is equals to 2 and more than 2 is the solution. More than 2 is the solution. I know that you already know about this Z-plane representation, where this is the real quantity and this is the imaginary quantity. If I try to make it more clear, let me draw a unit circle. This is the unit circle where this length is 1. Length is 1 means r is equals to 1. This represents anything, represents on the unit circle. On the unit circle means on the red line is basically representing the Fourier transform value. How it actually comes from the Fourier domain to the Z domain. Let me share that story. If I have for the Fourier transform, definitely this is relative frequency. This is 0. Let's say this is pi, and this is twice pi. So in case of Fourier transform, as I already mentioned that from the equation, the r is equals to 1. So there is no response from the r. So for a particular case, or for a particular xn, what we have found in case of Fourier transform, we just found that what is the frequency component we have in our unknown signal, and let's say that actually been represented here somewhere else here. So we have this frequency component, let's say omega 1. This is in between 0 to pi, and as you know that we have the same thing between pi to twice pi. We have the same thing repeating from pi to twice pi. Whenever we have omega 1, we also have another component omega 1, like here. It can be also extended in the negative side as well. I'm just putting it in the positive side. It will repeat like that. So now, if you think this is 0, omega, that actually been started from this point, this is omega equals to 0, this point. Now you are proceeding to the pi. Where is that value of pi? This is omega equals to pi. Where is omega 1? Omega 1 somewhere else. Let's say this is the point. Let me choose that color. This is the point where we have the omega 1. We are there. So we have some value over there. We have that frequency component. We got the frequency component from this xn. Of course, you can now understand whenever this omega is proceeding from the 0 to pi in the discrete time Fourier transform, in the z-plane, it actually been proceeding from 0 to twice pi, 0 to pi as well. Okay, so here it is a linear one, and there in the z transform we have the circular one. Throughout this circle, what is the value of r? The value of r is 1. Another thing, okay, so in the upper half cycle and the lower half cycle, they will repeat, so you can have this omega 1. And since you know that this is also a two-dimensional figure where you can put an arrow by which you can show that, okay, we have higher match with this omega 1 frequency to our unknown frequency xn, unknown component xn. So how we can show it in the z-plane, and there we have higher match means that is a pole location. So that's why we need to put a pole. So that means this is a higher value, that is a peak. It can be shown in a three-dimensional way, perpendicular to this imaginary and real this Cartesian plane. So that means you can put your pen upside down on this cross. So that means it shows a very higher value. It shows a very higher value. That means you have that component, and what is the value of r? So from there I can find that, okay, this is a critically stable xn. So from this figure, these pole locations, what I can find two things. One is the signal frequency is omega 1, and it is critically stable. So the signal frequency, I have found the signal frequency. This is the signal frequency, omega 1, and also it is critically stable because the value of r is equals to 1. And that is the representation of the z-plane. And now what I start earlier, that means if you have the signal, let me choose another signal which is unstable. Of course, this is not a continuous one. Just think that of course you need to digitize these things, so you have the digital samples only. So if you just consider that, let we have this kind of signal. Okay, so if I erase the black one, so you have this kind of signal. This is your new xn. This is your xn, which is definitely unstable, which is unstable situation. So it might be like this in a format of alpha to the power n un. It might happen that you have the step function where alpha is greater than 1. So to be very specific, we can take alpha is equals to 2. So then we can have 2 to the power n un. If this is your xn, the first question is, can you do the Fourier transform of this signal? The answer is no. Why? Because that is not stable. Because the summation, let me put like this, the summation for n equals to 0 to infinity, because un 2 to the power n, e to the power minus j omega n. I should write omega n. This part this part is not summable. That's why we can't do the Fourier transform. However, if we represent the Z transform, r to the power minus n, e to the power minus j omega n, in that case, what happens? We can write in a different fashion that, let me take it like this. Consider the value of r. We can also write divided by r to the power n, or we can write in a combined fashion that 2 divided by r whole to the power n. Now, when this part will be summable, that is the question. Of course, whenever this amount is less than 1, I should mark it here. If that is less than 1, then it is summable. So we can write 2 divided by r, that should be less than 1. So from there we can find r should be greater than 2. And of course, when r is greater than 2, for any value more than 2, in case of r, this function gives a stable situation. So if you do the Z transform, of course you can do yourself, and you can find the Z transform value x z of that function. So xn is equals to 2 to the power n un. If you do the Z transform, you can find 1 divided by 1 minus alpha z to the power minus 1. So you have done it before, so you can find this, and from there, if we can consider the things more in detail, we can find that we have z, and this is z minus alpha, that is the value. From there, we can find two things. What is the pole location? Zero location at 0, because z equals to 0. Pole location at z is equals to, so I can write z is equals to 0 at z is equals to alpha. This belongs to the location at omega, the location of the z, the value of the z is equals to 0, and here this shows the r, the magnitude of r, this is equals to, so the magnitude of r is equals to alpha. So in the pole 0 platform, what we can write with that notion, always I try to put the unit circle first. So this is the unit circle. What is the 0 location? That is at the center. You got it. That is at the 0 value. And where is the pole? This is at z is equals to alpha. So what is the value of alpha? That is for our case, that is 2. So this is the pole location. And if you put a circle with that, what are the other solution for the r? What are the other solution? That is a 2 plus all the value up to infinity. So more than 2 is the solution. As you already know that if your signal is a right-sided signal like 2 to the power n un, it's a right-sided sequences, the ROC actually covered the exterior of the circle covered by the pole having the maximum value, If you have more than 2 poles, more than a single poles, let me put another poles somewhere else here. Then you can also write a circle over this. So we have the solution outside of this unit, this circle as well. But where you got the common solution? The common solution is the outside of this pole. That means the exterior of the highest maximum valued pole will give you the total ROC of the Z plane representation. For example, if you have your xn is equals to 2 to the power n un plus minus 5, let's say minus 5 to the power n un. In that case, we can find that we will have, according to the last scenario, we can find two poles. Straightforward, we can write, we have two poles. One is at the location of 2 plus 2. Another one is at minus 5. And now you have two circles for the first figure. This is the circle, and you have the exterior is the solution, is the ROC. For the second one, let me choose a color like this. For the second one, you need a bigger circle. Okay, let me just think that, okay, we have the circle, and the solution is exterior. Then where is the common solution? The common solution is the exterior of the 5 value. So the ROC is equals to 5 to infinity. That is the ROC of the Z-plane. From this, we can understand about our signal. If we got the ROC, this is the unit circle. Let's say this is the unit circle, and you have the pole inside that for a causal signal. Causal means right-sided sequence for a causal signal. In that case, of course, the ROC includes the unit circle. That means it shows that R is equals to 1 is also a solution. In the solution plane, R is equals to 1 is also a solution. That shows that you have the Fourier transform, and that also shows that your system is stable. So from the very basic understanding, you can understand for the causal system, if we have the pole inside the unit circle, that is stable system. Of course, you know that. I'm just recapping the things. If I draw the unit circle again, if I have the pole outside the unit circle, it can be shown that for the, let's say, 2 to the power n u minus n. This is of course the anti-causal signal. That means it is a folded version of the unit step. In that case, the ROC is the interior of that circle. If that is the interior of the circle, again, it is stable in a sense, because in that case, the unit circle, this is the unit circle. The unit circle is also inside the solution plane. So you know about the stability perception for a signal where it is a right-sided sequence or left-sided sequence. In the right-sided sequence, it is the exterior, and for the left-sided sequence, that is the interior. It can be shown with the example. You can also do it yourself. For the left-sided sequence, it can be shown as here, like the range of the n is actually from -1 to -infinity, or you can say from -infinity to -1. Yeah, it could be fine. -infinity to -1. Then we have the value 2 to the power n, r to the power -n, e to the power the value minus j omega n. So if that is so, if we change the notation n with a -n, what will happen? It can be written as n is equals to 1 to infinity. So then that is 2 to the power -n, to the power -n, and r to the power now n, and e to the power j omega n. So in that case, so what would be the notation? It will be r divided by 2. So in that case, we can write r divided by 2 whole to the power n. Now, for which value of r this is stable? Definitely, all the values are So R should be less than 2 for make the system stable. So that means that shows that it is the interior. So if this is the 2 value, so the interior of that is the solution where the R is equals to 1, unit circle is this, and unit circle is also combined with the solution. So those are the recap from the Z transform. Particularly, if you have any problem with understanding with the Z-plane representation, the purpose of the Z transformation. If you have any question from the even from the bachelor study, you are very welcome to do the discussion, start the discussion if you have any question in your mind. I'll be very happy to discuss on those portion, because we have a mixed student group here, so we have different background definitely. So if you have any question or comments, okay, so of course your guideline is the book from the Procreus. So Prokis, you can go through that chapter. Probably the chapter is chapter number 3. So please go through that. I assume that you have already gone through most of the part of that chapter. However, you need to go through that again for understanding the basic of the Z transform. In this class, I always try to mention that don't be shy. So ask some basic question, no problem. So you probably think that you are the only person, you don't understand that, but it might happen that other people don't understand the same thing. So we can discuss together, and that will definitely help us because this class is for understanding. Okay. At this moment, do you have any question or any comments on the Z transform? So it looks very good. Okay, if I ask you one question here. Let's say this is the unit circle. And okay, unit circle, and let me draw some pole and zero locations here. This is a pole, and this is a pole, and we have another 0 at the center. Let's say center. Yeah. Can you draw the magnitude response from this pole 0 location? Let's say this is the representation from HZ. We have the poles. The poles are the imaginary poles, and as you know that the imaginary poles will come with pair. So that's why if we have a pole here, of course we should also have a pole at that location. So can you draw the magnitude response of HZ from this pole 0 combination? Just raise your hand if you can do it, because I know your response. By knowing your response, I would actually format my lecture plan. Who can draw the magnitude response by the pole 0 locations of the Z-plane? Mahbub, you should do that. 0, 1. Are you there, Mahbub?
Yes, sir.
Can you do that? You are not audible. Maybe some problem. We can't hear you because maybe there are some internet problem in your connection. Okay, 03.
Good, sir. Yes, sir. Stable today.
Rifat, I'm not sure whether my internet connection makes problem or your internet connection. I need your response. Can you hear me properly?
Yes, sir.
Yes. Okay. Okay, then it seems that I need to discuss on this issue as well. Okay, so let that we have this impulse response converted to the Z domain. If we want to find the magnitude response, Hz, magnitude response, it can be found that, okay, so let me draw the diagram first. This is the unit circle. If we have, there's a for a simple pole zero locations, let's say this is the 0 and this is the pole. We have single pole and single 0. For a particular moment, let's say for a particular omega, moment means particular omega, this is omega 1, the distance from the 0, if I put it the z1, because that is from the 0 point, we have the magnitude of z1 over the pole location, the distance of this pole location. So what is the distance? Since this is a P1, the pole locations. This actually gives us the magnitude response of this omega 1. So whenever the omega is moving, definitely these two terms, they are also moving. So they are this Z1 and P1, they are definitely the function of omega. When omega is changing, definitely they will changes their value. So let me draw this in the magnitude response curve. So if we can draw it in this way, reminder, this is omega equals to 0, this is pi by 2, this is a pi, and this is thrice pi by 2, and this is again omega is equals to twice pi. So if we consider this one, the omega is equals to 0 at that location, let me put that this distance is 0.5. If that is so, then try to follow these points. We are at this location now. What is the value of Z1 at that moment? The value of Z1 is equals to 1. So that is equals to 1 divided by, this is at omega is equals to 0. And what is the distance from the pole? That is 0.5. So that will produce the value 2. So that is the magnitude. So I'm plotting here, this is 2. When it is actually proceeding at some location like omega 1, it is in between, let's say this is pi by 2. Here is omega 1. At the omega 1, definitely the value, the Z1, it remains constant because it is always from the center. So we know that this 1 will remain constant. So that will give the value 1 always. Now what we are writing, we are just trying to find the omega h, the magnitude response at the location of omega equals to omega 1. So the distance from the 0 is 1, it remains constant, divided by the distance from the pole. So whatever the value, so you are putting that. So whenever you are moving to this point, now this is the 0 distance, this is the pole distance. Of course, this distance is now bigger than the previous one. So the P1 is increasing at the location of pi by 2. So it definitely increase. If that is increasing, of course, the overall magnitude will decrease. So let me put some value like here, okay, at this point. And whenever you are at this location pi, so that means you are at the location of pi, what happens? The distance from the pole, it is now 1.5. This is 1.5, and from the 0 it remains 1. So 1 divided by 3 by 2. So you can write this is it is, yes, 1.5 is 3 by 2. So it makes 2 by 3. So the amplitude is 2 by 3 here. So here we got an amplitude which is 2 by 3. So now if you plot all the points, then you can find this kind of scenario. Probably you can find this kind of scenario. So from omega equals to 0 to pi, you will get this scenario. This is the magnitude response of this Hz, where we have the pole at the location of 0.5 and the 0 at the center. And you can definitely replicate the whole things up to twice pi, and it looks like the same. Of course, the magnitude will be 2 again with some point. Okay, so we need to consider up to this. That is enough to understand the filter. What kind of filter is this? Of course, this is a low pass filter.
Low pass filter.
This is a low pass filter. Now, what we can do, we can this is your task. You can do yourself. If I change the pole location there and the 0 location at the same, you will find that if we go for the magnitude response, this is pi and this is twice pi. So you'll find that it actually works just the opposite of the previous one. And eventually, if you extend the concept, you will find like this. What kind of filter is that? Always we need to consider from 0 to pi. So it is, of course, the maximum value you will find 2, because this is at a minus 0.5. So you'll find the maximum value 2, and the minimum value is again 2 by 3. It is, of course, a low pass filter. So by changing this, the main motivation of this part of the lecture is by changing the or choosing the pole and the 0 locations, you can design your filter very well. If you consider this kind of scenario, this is unit circle again. This is the 0 location, and this is the pole location. Let me draw, okay, let me draw this one. So that we try to draw the magnitude response here from 0 to pi. Let's say this is pi by 2. Okay, so I'll write that approximately for this point at omega equals to 0. What would be the value? that would be 2 divided by 1. 2 is the distance from the 0 and 1 is the distance from the pole. So this is 2 by 1. So that is exactly 2. So we start with the value 2. Whenever you are proceeding there, you can find what is the distance from the pole and what is the distance from the 0. If you are proceeding more at the location of pi, what is the distance from the pole and what is the distance from the 0. So in two cases, we can find these two cases. If you consider these two cases, of course, this value, the distance from the pole, it remains constant. So no need to consider about that. So this is always 1. What about the numerator? It is now reducing. If this term is reducing, definitely this term is also reducing. And what is the lowest value you will get? You will get the lowest value is equals to 0 at omega is equals to pi, because at that moment the distance of the 0 is equals to 0. So if you consider this point, in that case, what is the distance of the 0? Of course, 0. 0 divided by 1. So that is 0. So at this moment, we'll got 0. So if you proceed from the omega equals to 0 to pi, you will find this kind of scenario. Okay, so it will definitely touches the 0 value of the pi at the location of pi. So if you consider the twice pi, we will have exactly the opposite scenario. That is the magnitude response of this kind of. What kind of filter is this? Definitely, this is a low pass filter. So by choosing the zeros or the pole locations, you can shuffle with the pole locations and the the type of the filter, whether you are choosing a low pass filter or the high pass filter. We'll talk about that with a lecture, probably in the next step. The other thing I should mention, since we have already talked about the, okay, so little bit more about this concept. If you have a multiple poles and the zeros, let's say we have 2 poles, 2 zeros and 2 poles. Now what happens? So let me give the name. Let's say we are at omega equals to 0 for that one. This is the distance. Let's say I put P1, and this is P2, and the distance, so state distance from the 1 0 to there is Z1 and another 0 to there is Z2. So the magnitude response is equals to, written as the multiplications between the Z, the multiplications of Z's, where the Zn, I can put n is from 1 to 2 because we have 2 values, and for the pole you need to do the multiplication of p n's, where n is equals to 1 to 2. Very simple format. For this case, it is equals to Z1 multiplied with Z2 divided by P1 multiplied with P2. This is for the multiple poles and the zero locations. It's a very simple. Okay. The same concept for the zero the phase plot. If we have the unit circle, let me choose the same example. Okay, maybe a different example could be fine. Okay. This is the pole. Okay, the zeros are there again, the same example. We have already learned about the magnitude response, how to find the magnitude response. Now, if we want to find the phase response, H, Z, the phase. Of course, that is also a function of omega for different cases. Let's say we are at this moment. In that case, just consider that I'm putting a line here for the zeros. I'm just putting 2 lines. What are the theta? So this is theta 1 and this is theta 2. I believe you understand what is theta 1 and what is theta 2. This is theta 2. So we need to write in this way, theta 1 plus theta 2. And take this little bit upper place to make it understandable. Here is the pole and it's a pole. Okay. This is the line. In that case, we need to line a horizontal line as well, where you can find the angle like this, and this is theta 3. And for the other one, you need to write a line over there and the horizontal line. And what is the theta? This is theta 4. So now you need to subtract those. So theta 1 plus theta 2, this is from the zeros, minus theta 3 plus theta 4. So that is how you can find the phase value. You can find the phase value for different omega. So you can find the phase response of a system. I believe this is very simple. So you can find the phase value. However, people are presenting those things by the equation. However, you can find whenever we'll talk about the filter design more specifically, then you will find that these concepts are very important whenever we are talking about the phase plot in the filter design. Because as you know that in case of FIR filter, FIR type, the phase is linear. The phase is linear. In case of IIR type, the phase is non-linear. With a very simple example, we can show it here. This is the, in case of, let's say, FIR type filter, you don't have any feedback. Since you don't have any feedback, you only depends on the input sequences. Like you are depending on xn or xn minus 1, xn minus 2, something like that. So in that case, you only have the, let's say, for hz, if I am writing in this way, h1 plus z to the power minus 1, what kind of filter is that? If I took the value, I can write z plus 1 divided by z, where the 0 location, this is of course a FIR filter, because if you extend the things, you have two samples. You have two samples, hn. One is 1 at the location of n equals to 0, and other value is 1 at the location of n 0, n equals to 1. That means it looks like this. So you have one stem there at n equals to 0, and another stem is here, n equals to 1, and this is your Hn. This is the impulse response where the magnitude is 1 and 1. So we have already designed this where the 0 location is at -1 and the pole location is at the center. Let me draw it in the red line. So this is the pole location, that is 0 location. So for all the cases, whenever you are having, you don't have any feedback, you always have the poles at the center. As you already know that in case of Z transform, always you have same number of poles and the zeros in a system. Sometimes it can be in the center or it can be in the infinite region, but you have the same number. So you can find that in case of FIR type, you always have the poles at the center. So whenever it is at the center, you do not have any impact. You do not have any impact of the pole because it is always 1. For omega equals to 0, omega equals to some value omega 1, omega equals to pi by 2, omega equals to more than that. So in all the way this value is it reflects the value is equals to 1, the magnitude, as well as whatever the phase. Now definitely the phase will changes. So if we talk about that, the phase, try to think in a way. So this is 0 degree and it also have the 0 degree. So 0 minus 0, that is at 0 at the location of omega is equals to 0. Now when you are at pi, you have different combination. So what is the combination? You have, let's say, what is the angle here, and this angle is increasing. So definitely it will increase. Similarly, this increment, since this is a circular notation, circular way, this increment is linear whenever you are changing the value of omega. The consequence will show that the phase of Hz will work in such a way that it is a linear combination or a linear procedure. So in the next class, we'll show that what is the phase. So you can draw it with a plot. This is of course from the Pythagoras rules or from the trigonometry. You can find the distance, and also the angle. So you can find for each and every cases what is the angle, for each case, and you can find what is the phase value. So whatever the case, this is increasing, this is also increasing, but the increment rate of this is higher. So that means if I have theta 1 from the 0 locations and theta 2 from the pole locations, it is increasing, but theta 2 is increasing more. That's why the overall phase of this system is decreasing linearly. And at omega is equals to pi, what would be the value? Can you tell me what would be the value? Omega equals to pi. So before that, you'll find, okay, so if I write it like this, this is just before that, omega equals to pi. At this point, of course, it is almost 180 degree. That means it is almost pi, and this value is very close to pi by 2, very close to, approaching to pi by 2. So at this point, what would be the value? It is exactly pi by 2, and this is exactly pi. So at At that point, the phase will be minus pi/2. And in the next day, we'll show that by the equation how it actually comes, the phase. So what we have learned today, we have learned, just make a summary of the Z transform, the purpose of that, as well as from the Z-plane representation, and from the Z-plane representation how to build the magnitude response and the phase response a little bit. So in the next class, inshallah, we'll talk more about the filter design to be very specific. Before that, I'll just try to give you a brief idea on the magnitude response and the phase response for a particular scenario, which can be mentioned as M point moving average. Okay, so that could be enough for today. So thank you very much for your attendance. If you have any question or comments at this moment, sir, we have more 5 minutes to proceed. Okay, it seems that you don't have any question at this moment. So let me finish today's session. Thank you very much.